about Link-Irregular digraphs.
So yep, just like you said, we're going to be talking about link-irregular digraphs, and we'll get into it in a minute, but link irregularity is kind of the opposite of regularity in graphs. So, there. So first, before we dive into this, what's a graph? A digraph's a type of graph, so first let's discuss what a graph is. Graph, just vertices connected by lines. That's really the entire concept of a graph. Very simple structure. When we talk about the degree of a graph, well, the degree of a vertex in a graph, how many edges are connected to that vertex. So this vertex is degree 3, so is this one, so is this one, so is this one. Since all the vertices have the same degree, we call this graph regular. Now, regularities over here, right, can have however many degrees, right? What's the exact polar opposite of regularity, right? So that brings us to irregularity. If no two vertices have the same degree, every two vertices they have different degrees, we call that graph irregular. Unfortunately, no such graph exists. So what's the next best thing? This brings us to link irregularity. It was introduced in 2025 by these mathematicians here, a paper in Discussions Mathematica, graph theory, and they introduced the concept. Not only did they introduce the concept, they proved like you have a fairly big family of irregular graphs. Yeah, for every value n greater than 6, you have a link irregular graph on n vertices. So it's a significant family of graphs to study. Later, Dr. Kermali right there and I proved some additional structural results on these types of graphs, which we published in a paper. And after that, we asked, what about digraphs, right? So you have, similar to regularity in graphs, you have regularity in digraphs. How do we bring link irregularity from graphs to digraphs? So we generalized these results, and that's what we're presenting here. When we talk about digraphs, right, all of the digraphs are orientations of simple graphs. So the earlier example of a simple graph, right, just put arrows on those edges, and that's a digraph. All right, so we'll begin with our definition, right? So let's suppose we have a digraph just like this one right here, and we pick any vertex of the digraph. The link of the digraph is the induced graph by the neighborhood. So what that means, for example, is take 1 right here. 1 is connected by an edge to 4, it's connected by an edge to 5, so 4 and 5 are its neighbors. We take 4 and 5, as well as any edges between them, so we have an edge from 4 to 5, and that's our link right here. Again, we have the link of 2, link of 3, link of 4, link of 5. Now one thing you might notice, no two of these links are isomorphic, right? These are both triangles, but the orientations are different. This is a circle, this is not a circle, in a sense. Same thing here, this goes this way, but this goes, this goes this way, but this goes this way, right? So since no two of the links are isomorphic, this is what we call a link-irregular digraph. And this, in fact, is a smallest example. If you have fewer than 4 vertices, there are no link-irregular digraphs. Sorry, fewer than 5 vertices, there are no link-irregular digraphs. So this 5-vertex example is a link-irregular digraph on the fewest number of vertices. So now we know what a link-irregular digraph is, we have some results, right? All right, so we've defined it, we've generalized the concept. So what can we say about them? First one, we had the existence theorem for link-irregular graphs, so similar existence theorem for link-irregular digraphs, right? Except this one's even nicer, n greater than or equal to 5, right? So we have one more number that we can have vertices than the link-irregular graphs. And in fact, actually, we have slightly stronger. So for link-irregular graphs, on 6 vertices, there's only one link-irregular graph. When we generalize that to link-irregular digraphs, any number of vertices, you have at least 2 distinct link-irregular digraphs. And so that is a very interesting result. There's no uniqueness dependent on the number of vertices. Just interesting observation there. And so now we'll get into some more structural properties now that we know like sizable family of graphs worth studying at least, right? So we want to find bounds on the number of edges. If we have a link-irregular digraph, it's on n vertices, how many edges can it have? Well, as you'll see later, there's no significant upper bound. The upper bound actually turns out to be trivial, the maximum number of edges we could have. However, we can find a lower bound, and turns out that we have the asymptotic lower bound here. That's found like fairly direct computation. If you want to see like the details of it, it's in our paper, but fairly direct asymptotic proof. And so we have this asymptotic lower bound, right? In graph theory, we have a result that any graph with more than, any graph on n vertices with more than, I believe it's 3 and minus 6 edges is not planar. That means however you draw the graph, you'll have overlapping edges. Well, since our asymptotic lower bound grows at n squared log n, faster than linear, all but finitely many Link-Irregular digraphs are non-planar. So that means finitely many are planar, but the rest of them, infinitely many, can't be drawn without crossing edges. So that's another interesting structural result of these graphs. A slightly more messy result. Using our earlier asymptotic bound, we adapted the proof of that, and we obtained these values. Essentially what this is saying is if every vertex has degree less than this, or every vertex has an out degree less than this, the out degree is the number of arrows pointing away from the vertex, right? Then the graph is not a Link-Irregular digraph. Just gives us a way to just immediately chop off a lot of graphs. And it follows from the earlier lower bound formula we found, proof of that, as well as degree sum formula and the pigeonhole principle. Fairly direct, just messy computations. So here's some structural properties of the graphs. Now, what about examples, right? We know these graphs exist, right? We just showed that we haven't shown any of them. But how about some interesting examples, right? So link irregularity, right? We had irregularity, but no such thing exists. So link irregularity is a weaker condition. It has to be weaker for such graph to exist. So since link irregularity is weaker than irregularity, one might ask if a link irregular digraph could be regular in any sense, right? So the first sense we consider is out degree. I believe it's out degree, yes, out degree regularity. So what that means is that every vertex has the same number of arrows pointing away from it. Have an example, right? This is 2 degree out regular, 2 arrows from each vertex, right? These ones, like that. So this is an example of an out degree regular, link irregular digraph. And one thing to point out about this though, is every vertex has the same out degree, but it doesn't have the same total degree, right? 1, 2, 3 edges on 3, but 5 edges on 4. So the underlying graph itself is not regular. What if the underlying graph though is irregular? Can we have a regular out degree on that? In fact, we can. So we have this graph right here, which is the fun graph, 9 vertices. It's a tournament actually, which means pick any 2 vertices. We have an arrow from one to the other. And this graph, a bit of a mess, is out degree regular, in degree regular, it's tournament, and it's link irregular. So that's an interesting example, right? Link irregularity is irregular, but you have to keep in mind the irregularity is in the structure of the graph, including the edges, when you're just looking at degrees, and when you're just looking at vertex degrees, you can have a very regular graph that is link irregular because they're different, slightly different concepts. So let's see. So here, right here, as we said, this is a link irregular tournament. So link irregular tournament exists, all right. So what about other link irregular tournaments, right? That's a very regular link irregular graph, so what about other link irregular tournaments like that? So first let's look, what's the minimum number of vertices we can find a link irregular tournament on? Well, turns out to be 6. It's this one right here. You can show by brute force, just looking at every single example, that you can't have fewer than 6 vertices for a link irregular tournament, right? So then, we just saw an example on 6, we saw an example on 9 earlier. So we have link irregular tournaments on 6 vertices, link irregular tournaments on 9 vertices. We proved inductively that there exists, not inductively, just a construction based off of this one with 6 vertices. that there exists a link-irregular tournament on 7 and 8 vertices too. So 6, 7, and 8, 9 vertices, none fewer than 6. And then we used a computer program to just see, well, what examples can we find? And for every value between 6 and 100, we were able to find with a computer program a link-irregular tournament on n vertices. So that brings us to our conjecture. Well, first brings up the question, for which value n does the link-irregular tournament on n vertices exist? And we conjecture that a link-irregular tournament on n vertices exists if and only if n is greater than 6. So this is kind of a similar result, actually, to our existence result from earlier, but it turns out to be a lot trickier to prove. We tried first an inductive approach, right? So we have one on 6 vertices, build up 7, 8, 9, 10. But it gets really messy to work with. And so 7 vertices works, 8 vertices works, but after that our inductive method starts breaking down. And then to find an alternative inductive method, you add a vertex. How do you add all the how do you decide which direction each edge goes? So it proves to be a very difficult result to prove inductively. So then what might work? We'll briefly outline one possible method here, and this will be pretty quick, so try to bear with me here. So in a previous work that Dr. Kamali and I did, we introduced the concept of a link-irregular labeling of a graph. So for here, we only need a link-irregular 2 labeling. So imagine we have a graph, lots of edges connected to each other. A link-irregular 2 labeling is a labeling so that if we have 2 isomorphic links, when we overlay them with each other, overlay them with each other basically, right? The colors essentially of the labeling don't match up. So a color-preserving map of the labels will not match. Try. Yeah. We can elaborate that more in questions, but essentially, any label-preserving map, there's no label-preserving isomorphism between 2 distinct links, and we call that a link-irregular labeling. We can generalize that concept to digraphs very easily, just bring the definition right over, and we have a link-irregular labeling of a digraph. And so our idea is to perhaps, we proved in our paper that there exists a link-irregular 2 labeling of the complete graph for all values n greater than or equal to 6. Those are exactly the values we want for our conjecture. Then such a link-irregular 2 labeling, if we just put that on top of an orientation of the complete graph, then we obtain a link-irregular 2 labeling of the digraph. So then what if we can show that when we change a color of the labeling, we can change the directions of the edges some way that we still have a link-irregular 2 labeling of the tournaments. Then once we do that, we can repeat it over and over again until we have a graph with just one color, a monochromatic graph that is link-irregular, and then that's our link-irregular tournament on n vertices. Since we had already proven that that a link-irregular 2 labeled tournament exists for all n greater than or equal to 6, this would immediately imply our conjecture, right? And in fact, this proof is equivalent to the conjecture. If the conjecture happens to be true, this proof will definitely work. So this is our possible outline of how we could approach proving this conjecture. It's proven to be a bit difficult of a way to approach, but definitely worth exploring. And that's all I had for you today. Oh, there. So thank you.